Good afternoon. I welcome you to this session of experimental methods in fluid mechanics, and today we will discuss the micro PIV analysis, which is an important measurement technique for the flow characterization at micro scale. If we recall that we have discussed about the PIV analysis, the operational principle, the method, and to some extent the post processing of the images. So, we are now familiar with the PIV, that is the PIV is the particle image velocimetry. If we try to recall, following this technique we can characterize the flow. That means, if you would like to measure the flow velocity, if you would like to obtain the pattern of the flow, then PIV, particle image velocimetry, is having a few advantageous features that we have discussed. PIV measurement is I can say a non-invasive measurement technique. For this measurement we do not require to disturb the flow field. Of course, which is essential, we need to consider, we need to select a few particles which are to be seeded to the flow, and the seeded particles should have a few important characteristics. Except this particular point, that the particles are to be seeded to the flow, there is no any other direct contact of any equipment, any measuring probe to obtain the flow characteristics. So, from that perspective, this analysis, particle image velocimetry, is a non-invasive technique. If we try to use particle image velocimetry technique in the paradigm of microscale transport processes to obtain the microscale flow feature, then we need to know what is micro PIV. That means, knowing, rather we have understood the PIV, if you would like to include this analysis in the context of micro analysis, microflow analysis, then do we need to consider any external feature or any other feature with the system, or if we can simply use the PIV setup to measure the microscale flow feature. Even if we can, then what will be the system components and of course the measurement techniques. So, here I would like to discuss a few important features of the micro PIV analysis. At the right side I have shown one figure where the flow velocity flow field inside a droplet that we have measured from our groove we have shown. So, through experimental investigations we have obtained the internal flow velocity field of a droplet using this micro PIV technique. So, when we will be discussing about this technique, it is rather it would be better if we obtain insights about the flow field, and that is why I have kept this figure. What are the important features of this particular technique? As I said, similar to what we have studied in the context of PIV analysis, here also this is micro. So, just one prefix is used, micro. So, this is micro PIV. We will see that for the micro PIV analysis whether we need to include, we need to consider any other features which is or are not there for the PIV analysis. So, this PIV micro PIV analysis, what we can see that it, if you would like to characterize the flow field, when we talk about flow characterization, that means we are interested in measuring the velocity profile, velocity magnitude, that means the quantification as well as the qualitative measurement of the flow. So, PIV micro PIV can micro PIV analysis can be used to quantify as well as to provide the qualitative measurement of the flow field. As I said, this is non-invasive flow measurement technique. Following this technique, we do not require to disturb the flow field except the incorporation of a few seeding particles. These measurements, important point to note, that is what I was now talking about, that I was talking about, that we have, if we try to recall for the post processing part, in the context of PIV analysis, in the context of the discussion of PIV, we have discussed two important aspects. One is the constructional feature of the setup, procedure, and finally the images which are captured using this technique need to be post processed, essentially to quantify the flow parameters. And for that I have mentioned many times that we need to have a light source, and that light source provide light which is used to illuminate a particular zone, and that is zone of our interest. And if we try to recall, then we will find that in the context of the discussion of PIV, we have discussed that light sheet. So, that means a sheet is on a particular zone, that means a sheet, that is what I have discussed, that a light sheet, and that is illuminating a particular zone. In the context of micro analysis, sometimes we need to go for the volume illumination. Instead of a zone, instead of a sheet, we need to go for the volume illumination. So, this is one important point we should keep in mind. Then optical access to the test section is required, that is obvious. Without light source we cannot measure the flow parameters using this method. So, we need to have proper light source, and that light source should have again a few important points to be fulfilled for this technique. High spatial resolution is important, because again I am telling, we are focusing our attention on a particular zone, and that is the zone of our interest, and we should have sufficient or high spatial resolution. And if we do not have, then we cannot track, we cannot quantify, or we cannot, even if we can, if we cannot quantify, and even if we try for the qualitative estimate, but if we have lack in spatial resolution, we will not be able to predict the qualitative estimate for the flow parameters. And finally, the images which are captured, again I am telling what is done, I will be discussing today again. Light is allowed to fall on a particular zone in the flow field, then images are captured, and light pulse which is used to illuminate a particular zone, there should be the duration of the light pulse should be something of the order of nanosecond or microsecond, and the gap between two successive light pulse which will be used to illuminate, that also should be very small. Now that means we will be capturing different frames of different images, rather images at different frames. Now the captured images will be used to predict the flow parameters, that is the velocity, that is what is important, and to do that we need to go for the autocorrelation or the cross correlation method. In the context of the discussion of PIV, we have discussed the difference between these two correlation methods, and we have briefly touched upon the cross correlation method in which is used in quantification of the flow parameters. So from the image which is shown here, it is clear that using this technique we can really qualitatively predict that the what we can see from this image, that the flow is radially inward. So what you can see from the direction of the arrow shown over here, that fluid is now trying to flow from outside to the inside, that is radially inward flow. This is the qualitative estimate. Also from the direction of the velocity and the arrow we can quantify the magnitude. So this is possible using this technique, and for that in fact from the color bar that was shown at the top of the image we can predict the velocity magnitude. So this method is I can say successfully can be used to predict the qualitative as well as quantitative measurement of the flow parameters. So this is a schematic of a typical micro PIV setup, that is very important to know, at least because we are studying PIV and again micro PIV, and what are the different components we have discussed. Today I was thinking at least to show a schematic, a typical schematic setup where we can see the different components which are integrated with this measurement method, and of course then we will try to discuss briefly their function. This setup I have taken from a journal paper. So only to this schematic will help us to understand what is done in the micro PIV analysis. So what you can see from the schematic is that one light source, I will be showing again the different components through block diagram in the next slide, but before I go to discuss that slide, at least I will try to discuss a few important points from the schematic. What we can see from the schematic is that at the top we have one syringe pump. So typically this is a typical micro PIV setup. So this is used to capture the flow parameters, micro flow parameters to be precise. That means we need to ensure that there is a continuous flow in a micro fluidic channel or micro fluidic pathways. So from the syringe pump is used to maintain a continuous flow through a channel whose length scale is of the order of micron, and the liquid is pumped and the liquid is taken from the other end into a sum that is shown over here. So this is essentially the sum which is collecting the liquid. So this is sum which is collecting the liquid, and this is syringe pump that is shown, and this is the pipeline, and this is the micro PIV micro channel. So this is the microfluidic channel, right. So our attention will be on this part. What we can see from the bottom, the setup, that is the experimental setup, which is the channel, essentially microfluidic channel through which liquid is allowed to flow using a syringe pump. This is inverted microscope. Now we have light source. So that is the light source, that is the light source. And this is double pulse laser, and this laser is used to supply light, and the light is taken through one filter, and then this is one filter, and then one lens, and there is an mirror which is inside the microscope, and that is also shown in this zoomed in view. So what we can see that this portion is shown through this zoomed in diagram, and we can see that the light which is coming from the laser, which is taken into a dichroic mirror, and this dichroic mirror has two important functions that we will discuss very soon. So the dichroic mirror allows a particular light of having certain wavelength to be illuminated, to be used to illuminate. So dichroic mirror use a particular light of having certain wavelength to be used in illuminating the fluidic path, and that is kept at the top, and that is shown over here. So this is the that microfluidic device system through which liquid is allowed to flow using a syringe pump. And since we can here we can see from the schematic again that as an essential prerequisite for this measurement technique is that we need to ensure that the liquid which will be allowed to flow through the microfluidic channel, our objective is to characterize the microflow parameters, then to estimate to predict the microflow behavior, then the liquid will be seeded with a few particles, and those particles will have a few important characteristics, that is what we have discussed in the last class. Now when dichroic mirror is allowing a particular light of having certain wavelength which is falling on the seeding particle, the particle will now reflect, the light will be reflected by the particle, and that will be again taken by the dichroic mirror, and mirror will allow that a particular light to pass, and it will be taken by a CCD camera, that is shown over here, and the camera will capture images at different frames, and the captured images will be now taken for further post processing using cross correlation algorithm to quantify the flow velocity. So this is what is the brief description of the microfluidic setup. I have taken it from the standard literature, and I hope the schematic is helped us to understand the basic process mechanism which is involved with the micro-PIV analysis. I have written something here that the spatial resolutions can be improved by imaging the flow field with high numerical aperture optics, such as each tracer particle is resolved to 3-4 pixels. And so now I will go to the block diagram where I will discuss the objective of different parts, that is the filter, then lens, why we need to provide this filter, why we need to provide this lens, and although I have discussed about the function objective of the dichroic mirror, but even then we will discuss what is done essentially using this dichroic mirror. Okay. So, this is the block diagram, the flow diagram of typical micro-PIV process. I have explained in the previous slide that light is taken from a light source, it is taken into an excitation filter. So, this filter is essentially an excitation filter. So, this is I didn't write. So, this is excitation filter. Excitation filter. Now, then if we consider only white light is coming, if the light source is not laser, that is laser is very costly. If the lights the source of light for the investigation is laser, then we will get the monochromatic light. For that we do not require this excitation filter, but if this is not the case always, because laser is very costly, and if we use white light, then the light is taken into a excitation filter. The objective of this excitation filter is only allow a particular wavelength, say green light. That depends whether whether we need only the green light or we need red light. That will depend upon the particles which we have considered to seed the flow. That is the particles which we have considered for the measurement method. So, the particles which are seeded to the flow will eventually depending upon the particle characteristics which are seeded into the flow, we can select this excitation filter. Now, the white light which is coming from the light source, it will be taken to the excitation filter, and for this particular case, and it is I can't say this is the case which is true always, but it is normally taken that excitation filter will only allow the green light to pass, the wavelength of the green light to pass. And if I now go back to the previous slide, after the excitation filter we have one lens. So, what is the objective of the lens? Lens is taken so that, since our objective is to analyze, to characterize the microflow, then the confinement of the microfluidic device is very small, of the order of micron. So, our objective should be, and that too in the context of microflow, we are focusing on a particular volume. So, it is not expected, rather it is not advisable that the light which is used to illuminate the microfluidic device for this purpose should focus only the zone of interest. So, to ensure that the light which is coming from the excitation filter, that means the light will now focus on a focal length, on a that is to ensure on a focal point. So, the light which is taken from the excitation filter, which is now taken into the lens, only to ensure that we can focus a particular zone, particular point rather. So, for that this lens is taken. So, that means light will be splitted into two parts, and the splitted light will be allowed to focus a particular zone. Of course, there will be some kind of I can say plus minus level range of uncertainty, but even then it is not advisable that light should be either light will only focus the our zone of interest, and for that lens is taken here. Then after that light is taken to the dichroic mirror. As I said, the dichroic mirror is having two different objectives. First one, if we now come to this slide, the green light which is now coming, which is falling on the dichroic mirror, the dichroic mirror will now reflects the green light to the objective lens. That means this is our objective lens. So, this is our objective lens and this green light, the dichroic mirror will reflect the green light to the objective lens. So, that means the light is coming. Now, again we need to focus that light on the objective lens through the objective lens into the zone of our interest. So, the dichroic mirror will do this job. Now, when the light is coming to the objective lens, then the objective lens is now responsible to direct the light to the specimen, to the zone of our interest, to the object. So, that means now we are illuminating. So, now if I go to the previous slide, dichroic mirror is now allowing green light, rather reflecting green light to the objective lens. If I say that dichroic mirror is allowing green light to fall, to illuminate the green light to fall on the object, to the specimen through the objective lens. So, the green light which is coming from the excitation filter, that will be reflected by the dichroic mirror, and the reflected light will now illuminate the object, our specimen through the objective lens. Then our specimen is micro specimen, and that is there is a continuous flow. So, we are focusing on a particular zone, and there are few particles which are seeded to the flow. So, when we are focusing a particular zone, a particular volume using the light, we are essentially focusing the light on those particles which are in the flow, and these particles are basically fluorescent particles, and when light is coming, the particles will emit lights and say the red wavelength. So, green light is now falling on the fluorescent particle will now emits light, and the light is having wavelength red. Now, the light will again come to the objective lens, through objective lens it will be now direct to the dichroic mirror, the reverse path, same path but in the reverse direction, and then dichroic mirror. Now, objective of the dichroic mirror is that earlier dichroic mirror allowed the green light, rather reflected green light to the objective lens. Now, the reflected light which is coming from the fluorescent particle will be now coming through objective lens into the dichroic mirror, but now dichroic mirrors won't allow light to be reflected, rather now dichroic mirror will only allow light to pass to the lens. So, that is what I have written, dichroic allow only red light to pass through the restricting sphere lights to the lens, and lens of what, that is the if I go to the previous slide, CCD camera, and ultimately the lens focuses the light on the sensor, and ultimately we capture image, and the captured images are now taken for further post processing, essentially to quantify the flow parameters. So, this is what is the typical I can say process, rather steps I can say of micro-PIV measurement. Now, the main components of the micro-PIV setup, what is important, again I am telling, seeded particles. I have discussed in the context of discussion of PIV that the seeded particles will have a few important features. Again I am discussing a few of them, that it is neutrally buoyant. That means the seeded particle will largely follow the bulk flow, and the density of the particles will be almost equal to the density of the fluid. Here one important point I have mentioned, that very low relaxation time, which is characterized by the Stokes number, and that means Stokes number will be very less. What is that? So, if I try to draw here. So, if I say this is the velocity u and t. So, what is relaxation time? The Stokes number is defined by the as the ratio of relaxation time to the flow characteristics time. We know the flow characteristics time from our undergraduate fluid mechanics knowledge, but relaxation time now when the fluid is start flowing, say we are just switching on the syringe pump. If I go back to the if I try to recall the schematic which I have depicted in the previous slide, that the moment when syringe pump is allowed to syringe pump is allowed to run, then liquid will start flowing through the microfluidic device channel. Now, the particles are also in the rest. So, if the particle inertia is very high, then what will happen? So, if I switch on the syringe pump, liquid will now start liquid will start to flow through the fluidic confinement, and the particles will also starts flowing with the liquid, and that is why we can ensure that the velocity of the particles will be equal to the velocity of the flow. If we try to recall again, I have discussed in the context of my PIV discussion that in this technique essentially we are essentially measuring the particle velocity, particle which are seeded to the flow. So, by measuring the velocity of the particle, we can predict, we can correlate the velocity of the fluid. When we can now when the liquid is start flowing, ideally particle will start immediately to flow with the liquid, and that is why they are neutrally buoyant. But in reality that is not so. We need finite, although of the order of micro or nano, but we need finite time gap, that the moment when syringe pump switch is on, then liquid will start to flow through the microfluidic device, particles also will start to flow, but liquid will start to flow, and say I am drawing this will particle velocity is initially 0, liquid velocity is here. So, it will take certain time to reach the liquid velocity, and then liquid velocity and particle velocity will be equal. So, if I say this time t r. So, if this is the velocity of the liquid that is set by the syringe pump, particle velocity is initially 0, the particle will take finite time which is of the order of nanosecond, but even then this time which is taken by the particle to move with the flow, and this time is known as a relaxation time. So, what we can see from this understanding that this time will be very small, smaller this time we can ensure that the particle will largely follow the bulk flow, and that is why the Stokes number will be very small, and that is what I have written, much less than 1. Finally, the random thermal noise in the flow field should be minimum, and that is one important point for the measurement technique using light. Next is lighting arrangement. So, here are a few important points, that high density monochromatic light is preferred. Considering this point, laser light source is preferable for this measurement technique. Generally, high powered laser beam with short pulse duration is preferred. Again, I am telling that laser is used to illuminate, and we are having pulse laser, that means it will illuminate, stop, then again illuminate, stop, like this, kind of time periodic, but the time gap between two successive light pulses will be very small. Otherwise, I mean, because our objective is to measure the velocity of the fluid or the flow velocity, we need to seed a few particle to the flow, and what we are doing, we are measuring the velocity of the particle. So we are focusing a particular zone. What we do, by focusing a particular zone, we say that the particle location is a few particles will be captured in the first frame. Second pulse will come, we will capture the second frame. A few particles which are captured in the first frame of reference will be there in the second frame of reference. Only then we can calculate what is the distance traversed by the particle which were there in the first frame are now in the second frame, and from there we can calculate delta x and delta y, and I know the time gap between two successive laser pulses, and from there we can correlate what will be the velocity. Now, to ensure that if the flow velocity is sufficiently large, then our duration of light, to ensure that the same particles will be there in the second frame of the image which is captured in the second frame, our duration of the light pulse between two successive light pulses will be very small. So that is why short pulse duration of the laser is preferred. Sheet illumination is not possible due to micro size length scale, thus volume illumination is carried out in micro PIV. See, this is an important point, and that is what I was talking about in the beginning of this class, that in the PIV analysis we are focusing on a particular area, not volume, that is a sheet illumination. But for the micro PIV analysis, if we just try to illuminate a particular small area, then it is very difficult to ensure that a sufficient number of particles will be there in the fluid in that particular zone, and that is why it is better to illuminate the volume, so that we can have at least sufficient number of particles present in that volume, and the entire objective of calculating flow parameters will be ensured. And final point is the depth of field should be lower than the depth of flow. That is very important. Distance of point source of light can be displaced from its focal plane, producing a focused range in acceptable range. To explain this, what is the meaning of this? The depth of field should be lower than the depth of flow. If the depth of field is larger than the depth of flow, what will happen? That is what I was explaining, again I am telling. If we try to illuminate a particular portion of a microfluidic confinement through which a liquid is flowing, instead of focusing the required area, required portion of that microfluidic confinement, if we try to focus, rather if the light source is such that it is focusing larger, then what will happen? The calculation of flow velocity or flow parameters will be erroneous. Why? And because the particles which are there in microfluidic channel, the confinement, because of the very small narrow confinement, the zone itself is very small. Now, instead of focusing on that particular zone, if you try to, rather if the light source is such that it focuses little bit larger area, larger zone, then the calculation may not be the correct one. What is done to ensure that the light which is coming from the light source, which will be taken to the lens, and it will try to focus the required portion, rather it should focus the depth of the flow. If it is equal to the depth of the flow, it is okay. If it is higher than the depth of the flow, there will be error in the results. It is always better that the depth of the light should be always less than the depth of the flow, so that our objective of accurate prediction of the, rather quantitative prediction of the flow parameters will be justified. Next is, and if we try to recall the schematic, the main components of the setup is, one is light source, and finally we need to capture images, and from the captured images through the post processing algorithm numerically we can predict the flow parameters, and to capture the images we have camera. Now we have CCD camera, that is what I have discussed in the last class, that is charged coupled device. If it is CMOS camera, complementary metal oxide semiconductor camera, it is also fine, and this both enable high speed imaging. Our objective is to ensure high speed imaging, and time between two successive laser pulses is very small, and we need to ensure that the two different images at two different frames will be captured. What I was discussing in the last lecture, that velocity calculation using algorithm. I have discussed about the difference between autocorrelation and cross correlation algorithm, and from the discussion we have understood that the autocorrelation algorithm is not desirable nowadays, because if you use autocorrelation algorithm in one when we capture image, one frame we have one camera, then frame is advanced, right, and in autocorrelation both the initial and final position of the seeding particles are recorded in the same frame. If we record in the same frame, then very difficult to identify which was in the first and which was in the second, and to avoid that the cross correlation algorithm is used. What is done is cross correlation algorithm, that is what I have written in the last lecture. If you try to recall what is done, that flow field is illuminated, image is captured in the first frame, right, camera frame is now advanced, and the final positions are recorded in the second frame. So if the first frame it is for the one dimension, only for the understanding, for the ease in understanding this first example I have taken, where the first frame which is say only the, I would like to say this only the function of x. So the particles are moving only in the x direction. I have taken this example again, I am telling only to have our understanding in a effective way. So the first frame which is represented by a function f, which is function of x, one dimensional. Second frame, the image is represented by a function g, what is seen from the schematic. What is done in the cross correlation algorithm? In the cross correlation algorithm, particle seeding images which are divided into different zones, those are known as integration windows. That is what we have discussed in the last class. I am not going to discuss all those things again, but what is done, seeding images in the flow field are recorded in the first frame of the camera, that is represented by a function f in this plane, right, and camera frame is advanced, and the final positions are recorded in the second frame, and which is represented by g in this plane, right. Now these two images are post processed following the cross correlation algorithm, essentially to measure the velocity. What is done? I have written in micro-5G individual particles are not tracked, rather the shift in the pattern of a particular integration window is tracked. So for two typical function fx and gx, I mean one dimensional cross correlation between, so we have captured the first frame f, they are advanced, they are moved now by an amount psi. So in the second frame it will have gx plus psi, and transforming from x to x minus psi, that means I have captured image in the first frame, this is now advanced, and another that is what the final positions another image which is captured in the second frame, that is G. Now we are advancing F and we are trying to find out, the particles which are there in the F, where we can find out these particles in the G. So that is where we are advancing. That is what is done in the in actual process. So F is now advancing. Now when F will be now in the G, that means when two function overlap, so that means F we have captured, we are slowly advancing. So particles are there in a space with time flow progresses, particles are moving, we are capturing second image. That is what we did in the image in the microfluidic technique. So we are trying to represent all those events in the numerical platform, essentially to track the particles which are captured in the first frame, and from there we are trying to calculate the velocity. So the F which is captured in our advanced and trying to find out the F in G, and that means now when we are advancing F and when it is approaching to G and when these two overlaps, we will find P, when we will find the peak, and that is the cross correlation algorithm. If we try to, when we ensure that there is a peak, then from there we try to find out what is delta x. If I know the time between these two successive laser pulses and between two different images. Now if I know the delta x, that is peak is there, and from by knowing the delta t I can obtain the u, that is nothing but delta x by delta t. So this is the cross correlation algorithm. That is what I have discussed in the last class, but today in the context of micro PIV, that is I am discussing again. Now if we go to the next, so the peak are achieved when two function overlaps. These peaks help in determining the relative shift of the integrated point. So that means our point, I mean the first frame we have divided into a small number of zones, integration windows. We are now advancing the first frame, and when the first frame is advancing and it is overlap with the second frame, we will find peak. By knowing the peak, we will sure certain that there are the particles which are captured in the first frame and which are there again in this frame, and from their peak we try to obtain the relative shift of the integration point. If we now calculate, if we can predict the shift, from there we can calculate what will be the what will be the velocity, that is velocity is nothing but delta x by delta t. So this is again in the first case I have taken one dimensional case only for the ease in the understanding. This is again for the second two dimensional case. So instead of only f x, here the function is f x and y and g x and y. Similarly transform x is equal to x minus psi and y to y minus eta, and the same procedure is adopted in this case. And finally for a finite integration windows, we use this equation to track this delta x and delta y. So when these two functions overlap, so if it now consider this function, so initially you are considering f x and y, camera frame is advanced, second frame g x and y, the first frame is now advanced, and when it overlaps with the g x y, we will find the peak value, peak x and y, peak of x and y, and if from the peak we can measure, we can calculate, we can measure the shift in the integration point, and the shift in delta x and delta y of the integration window in the x y direction respectively at a time interval delta t, and that is what we know. Time interval delta t we know because the delta t is the time gap between two successive laser pulses, or between the gap between two images captured. We know, that is we know from our experimental analysis. So knowing delta t a priori, we have calculated delta x and delta y. From there we can calculate u and v, that is nothing but delta x by delta t and v is equal to delta y by delta t. So to summarize today's discussion, our objective was to characterize the microflows, to obtain the microflow velocities, if it is two dimensional, so or if it is three dimensional. So starting from the basic process, basic mechanism of the PIV analysis, what are the different components different components present in the micro PIV system and also identifying their role, their objectives. We have discussed today the PIV PIV analysis, the process of the PIV micro PIV analysis, and we have tried to discuss the post processing algorithm which is used to predict the flow velocities from the captured images, and we have seen that for the one dimensional as well as two dimensional, and this process, this method is equally applicable for the three dimensional case as well. We can calculate the three dimensional velocity in three dimensional as well in the microfluidic confinement. So, from there we can quantify the microflow velocities, and also we can qualitatively estimate, that is what we have seen from the schematic depiction from the figure, that is what I shown in one of the slides in today's presentation. So, this micro PIV analysis is again I am again telling that the micro PIV analysis is very important and sophisticated method in characterizing the microflows, to be precise in measuring the microflow velocities, and for the prediction of the flow behavior, microflow behavior, both qualitatively as well as quantitatively. So, with this I stop my discussion today, and I will continue my discussion in the next class. Thank you.